Hi everyone, I am Osman Hakyemez. I am a second year electrical and electronics engineering student. Today I will be presenting you my Physics 212 modern physics project titled as the relativistic momentum and energy relationship of beta particles. In this experiment, we are going to test the motion of the beta particles in a magnetic field, and we will be discussing we will be experimenting the relativistic approach and the normal approach, and we will be comparing the results of our experiments in order to get a better vision of the relativistic energy momentum approach. First of all, in theory, at relativistic speeds, classical mechanics breaks down a little bit, and instead of the classic energy equation of E equals to 1 over 2 mv squared, we have another definition in the special relativity that tells us energy square is directly connected with the momentum times speed of light square, and also this is in addition to the masses square and the speed of light's fourth to power of fourth. And this leads a relativistic expression of for momentum that I will give in here. The magnetic force on the charged beta particles bend their path into arcs. From this curvature, the radius, we can extract the momentum as this. In non-relativistic approach, we have it on the left side, and also we have the relativistic approach on the right side, which we will be trying to test which one is the which one actually. And this is our setup. We created the setup with 6 stacked ferrite magnets that generates a strong uniform field around uh, around 80 milliteslas. And also we created a Geiger-Müller counter for detecting the beta radiation, and also we designed a 3D printed PLA housing. We did created some steel collimators and 1 millimeter aluminum slit to limit the angle of the emission, and also we had a SR90 radioactive source which we controlled carefully, and also we used Arduino to interface the data and serially monitoring it in our computers, and we measured the magnetic field around 83.56 millitesla with using Gauss meters, and also our theoretical beta energy was 546 kilo electron based on the SR90's decay. In our procedure, we get the data with using the Geiger-Müller detector in 1 centimeter steps. We moved it, and we recorded the count rates for every point. And also, we found that the maximum lateral distance, D max, before beta counts drop to background level was 8.5 centimeter. Using our geometry, we calculated that our measured radius is around 4.15 plus minus millimeters, 2.5 millimeters, which is larger than the both relativistic and non-relativistic approach. But we are a little bit closer to the relativistic approach. The measured radius aligned more closely with the relativistic prediction, confirming that the classical model fails at high velocities, and we had a little errors due to non-uniform magnetic field in the central region, because we had non-uniformity at the corners and at the sides actually, that affected our data. And also step size of 1 centimeter was a little bit limiting our resolution, so we also had a little bit around error because of it. And also we had lots of background noise actually, and we tried to mostly suspend it, but as much as possible we did it, but it is not that much possible for like sophomore student. So But despite these, the results were really supporting this special relativity actually. Thank you for watching. This project demonstrated a good hands-on approach on the relativistic approach, and we understand that how the beta particle acts in the magnetic fields, and we try to contribute to the general science society as much as we can. Thank you for watching, and this was an undergraduate level experiment of relativistic and non-relativistic approach comparison.